Watching this lesson, you're watching my lesson on viscosity and density in the mix and flow of matter unit. This lesson will focus on, as I mentioned before, viscosity and density. So let's go to presentation mode, and hopefully it'll work. There we go. So we're going to talk about viscosity first. In a nutshell, viscosity describes how thick a liquid is, how quickly it flows. And this picture of maple syrup is to give you a visualization of what viscosity is. Imagine pouring a bottle of maple syrup. Does it pour quickly? Does it pour slowly? Or somewhere in the middle, right? And hopefully you realize that maple syrup doesn't really flow that quickly. So viscosity is how quickly or how easily the molecules in a liquid or gas move past each other. Viscosity is how easily do the molecules move past each other, right? Thicker liquids, really thick liquids like maple syrup, honey, wax, they tend to have bigger molecules. They tend to have more complicated molecules. And so when you pour them, those molecules bump into each other, and that slows them down. So they pour slower. Here we have wax or honey being poured down and collecting at the bottom. Now, if this was water, it would pour really quickly and spread out. But here we see this picture showing that it's pouring slowly and it's collecting here. It's not even spreading out, it's just sort of collecting here. And a similar thing would happen if you did that with maple syrup. Maple syrup pours relatively slowly. So that would mean that these chemicals, these substances, have molecules that are very big or complicated, and so they bump into each other and they flow slowly. If you were to say something is viscous, then you're saying that it is very thick. You're saying that it flows slowly. You're saying it has a high viscosity. You're saying that the molecules move slowly past each other. Flow rate is kind of the opposite of viscosity or viscous. Flow rate is how fast a liquid flows. So if you have a high viscosity, then you should have a low flow rate, right? A flow rate determines how fast a liquid flows, or how fast the liquid flows, yeah. And viscosity is how difficult it is for the molecules to move past each other. So if you have a high viscosity, the molecules are moving really, really slow. So it's going to flow really, really slow. So it's going to have a low flow rate. But because the molecules can't move past each other very easily, it has a high viscosity. Water is the opposite. The molecules that make up water aren't so complicated. So that means that the molecules in water that make up water flow past each other easily, meaning that water has a high flow rate and a low viscosity. An example of viscosity and liquids that have different types of viscosity, like understanding viscosity used in society, is nail polish. This is a chemical that we use to color our nails on our hands and feet in order to make them look nice. But in order to make nail polish, you need to understand how viscosity is used or how viscosity works, right? If you have a very high viscosity in your nail polish, then the nail polish will be very thick and goopy. And so it wouldn't spread very easily, right? And if you have a very thin nail polish or a very low viscosity nail polish, then it'll be very runny and it'll flow off your fingers and won't dry and again won't work. So you need a right balance of viscosity and flow rate so that you can create a nail polish that actually sits on your nails. Nail polish is a mixture that starts out a little runny, it's not super thick, but over time the solvent in the mixture, the liquid in the mixture, evaporates. And that evaporation leaves behind the residue or the solute. Just like with salt water with dehydration. You heat the water evaporates, and what's left is the residue, the salt. Here, the nail polish is put on. It starts out like a liquid. The liquid evaporates, and what's left is the pigment or color. And again, you need the correct viscosity in order to have this chemical do its job. Otherwise, it'll be gloopy and uneven, or it'll be runny and slippery and won't stay on. So different liquids can have different viscosities. That's because different liquids can be made up of different kinds of molecules of different sizes, right? Maple syrup has one or a few types of molecules in it that are very large, while water really only has one type of molecule and they're relatively small. So liquids with really large molecules, well, those molecules tend to bump into each other. And so when you pour liquids with large molecules, then their flow is slowed by the fact that they're bumping into each other. While liquids like water with small molecules, well, there's less chances of those water molecules bumping into each other. So the water moves past each other very easily, and so it flows quickly. A good example is molasses. Molasses is a sugary liquid that's used in baking, and it's very thick. The molecules that make up molasses are very big and complicated. And so the liquid flows very slowly down from this spoon down to the plate. So is there a way to increase the flow rate of molasses? Well, if you remember from our previous lessons, what we're asking in this question regards the movement of molecules. And what affects the movement of molecules? Energy. Energy affects the movement of molecules. As you increase the energy of anything, the molecules will move quicker. So if you want to pour molasses quicker, you want the molecules to move quicker. And so to make the molecules move quicker, you add energy. An example of energy that is readily available is heat. Heating liquids decreases their viscosity, right? It decreases their viscosity because the molecules can now move past each other quicker because they have more energy. The liquids vibrate or move faster so that they can push past each other quicker, and so they flow faster when you add heat. Right? And then the opposite is true. If you take away heat from a liquid, you're increasing viscosity because the molecules are moving slower. So they have a harder time moving past each other. So for liquids, heating them decreases viscosity and increases flow rate, while cooling liquids increases viscosity and decreases flow rate. With gases, gases can be affected by viscosity and they have flow rates, but the rules for their viscosity and the rules for their flow rate are flipped, right? So if you heat a gas, their viscosity will increase. And if you cool a gas, their viscosity will decrease. Well, that seems kind of counterintuitive. That doesn't seem to make sense, right? Why would it work for a liquid? Why does it work for a liquid to heat it up and have the molecules move faster? And so they move faster, so they pour faster. That just makes sense. Well, this doesn't seem to make sense for gas. The reason is, again, if you go back to our states of matter, we realize that solids have the lowest amount of energy and they don't move so fast. And so you can't pour a solid, right? You can't pour ice. It's just a block that falls out. While liquid water, regular old water, can be poured, right? So adding a bit of energy to ice melts it, making it a liquid, and they have a bit of energy and they can be poured. But adding more energy can cause the water to evaporate and result in water vapor or water gas. And this water vapor, well, it's already moving really quickly. You've added a bunch of energy. Gas already has a ton of energy. So if you add more energy, then you have too much. You have too much of a good thing when you want to pour it. Because now when you want to pour this gas, the molecules will bump into each other and crash into each other more and knock each other out of the way. And then they can't pour into another container. So gases become more viscous with heat because they have so much energy, the molecules crash into each other. And that's it. Because the gases already have so much energy, they crash into each other. And so their movement is slowed because they have too much. Density. Density is an important term you need to know. All density is how much matter is in a given space, how much stuff is in a space, right? So if you have a really crowded area and all the molecules and all the particles are really, really close together and there's very little space in between the molecules and particles, then you have a high density. If there's a lot of space, there's a ton of space between the molecules and particles, then you have a low density, right? These two pictures are the same size, relatively. But there are more of these particles in this space than over here. So density refers to how much stuff, not using scientific terms here, but how much stuff or matter is in a given space. And if you have a lot of stuff or a lot of matter in a space, then you have a high density. And if you have a lot of space between your particles, right, then you don't have space for more particles because they're disorganized. There's too much space between them. So you have a low density. They're loosely packed. So an example we can talk about with high density are diamonds. Diamonds are some of the most high density things on Earth because those carbon atoms are squeezed so tightly together and so compact that they're very dense and makes them very hard. Well, an example of something with low density would be wood. The molecules are arranged loosely, like with some order, but there is a lot of space between the molecules and the atoms. And so you can squeeze wood, you can compress wood. And so wood relatively has a low density. So when we talk about states of matter, which has the most density? Solid, liquid, or gas? Well, again, if you combine what we talked about with flow rate as well as states of matter and energy, you'll know that, well, when you add energy to a solid, they start to move. Well, when they move, they start creating space in between the particles. And so they become less dense, right? They're taking up more space because they're moving out more. And if you heat a liquid up even further, well, the molecules are moving even further out, and they have more energy, and they're moving away from each other. So you have even less density. So gases have the lowest density of the three states of matter, and solids have the most density, right? If we look at iron, for example, solid iron is very dense. All the atoms of iron are closely packed together. If you melt iron, they take up the molecules, the atoms, they take up more space, and so they spread out. So let's say we had a kilogram of iron, an iron bar that weighs a kilogram. Okay, well, all the atoms in here will be tightly packed, and so this kilogram of iron won't actually be that big. But when you melt it, the atoms move out, and they take up more space. And so liquid iron, a kilogram of liquid iron, will take up more space. But you don't have more iron, obviously. It's still a kilogram. So that means that you've decreased the density. There's more space between the atoms than in a liquid than in a solid. So as something is heated, the particles will move outward with more energy. The particles take up more space but have the same mass, right? You're not adding more, you've just changed the state. And that change of state changes how much space that whatever you're using takes up. If something takes up more space but does not gain mass, does not weigh more, then it's become less dense. There's more space between the atoms and molecules. How to tell if something is dense, or how to tell the density of something? Well, density is how much space a type of matter takes up. So you can look at the mass, in our example we had iron, and the volume, right? So you weigh how much whatever you're using is, you just weigh it out. And then you look at how much space it takes up. So mass is the total amount of matter, and the amount of space taken up is the volume. So it's mass divided by volume gives you density. And the way I like to look at it with a triangle, you may see this later, I like to do this. It's a terrible triangle, I know. Right? So we have mass, so we put mass at the top of the triangle, right? Divided by volume equals density. And I'll put D for density, right? And using this triangle, you can figure out how to calculate any of these three things. So mass over volume, mass divided by volume, gives you density, what's left. Let's say we were looking for volume. Well then, mass divided by density gives you volume. Let's say we're looking for mass. Well, we have volume and density, volume times density. And we'll go over this in more detail. So here we have an example. An object of 10 grams has a volume of 2 centimeters cubed. What is the density? Well, if you go back, density is mass over volume. So what is our mass of our object? It's 10 grams. Now, for tests and things, please make sure you have your units. Don't forget your units because that's very important. Divided by 2 centimeters cubed. So this is our volume. So we go 2 centimeters. Oh, well, that was terrible. Centimeters cubed. Right? So 10 divided by 2, we have 5 grams per centimeter cubed. Sorry, this is terrible looking, but yeah, I don't have a tablet. So 10 grams divided by 2 centimeters equals 5. 10 divided by 2 is 5. And we have grams per centimeters cubed. So that is our density. This is our density of our object. 5 grams of whatever it's made out of per centimeter cubed. So complete this table. You have an aluminum amount of aluminum of 5.4 grams. And you have a density of 2.7 grams per centimeter cubed. So we go back to that triangle I drew, right? So we draw this triangle, right? Like so. Or, sorry, let's do that again. We draw the triangle, like so. And we have mass on top, right? And we have volume at the bottom. And then we have density over here. Okay, that's an ugly M, but that's an M. So we have mass, we have density. So we have mass, we have density. But in this triangle, we see mass over density. So we'd go this mass divided by this density gives us this volume. So I'm not going to write it down. You can figure that out on your own by following along with these steps, right? So here we have salt, and we're trying to find the mass of the salt. If it takes up a space of 3 centimeters and has a density of 2.16. So again, we're looking for mass, so mass is over here. So it's volume multiplied by density, volume multiplied by density, which gives us mass. And I'll do the last one, third, copper. We have mass, again. We're looking for that, and we have 5 centimeters cubed of copper and 8.92 grams per centimeter cubed. Again, we're looking for mass, so mass is here. So we have volume and density, volume times density, right? If they're above each other, if one is above the other like this in the triangle, then you do the top divided by the bottom. But if they're across from each other in the triangle, you just multiply across, and it's easy. Again, one last time, one more. Oak, we have this type of wood. We have 0.33 grams. I didn't put the unit on it, shame on me. Grams. And then we have the mass. So we have the mass, the volume, to the density. Mass, volume, density. So we go mass divided by volume gives us density. And then we put that there. So try and work on this on your own. This type of question probably will show up on a test. So please know how to calculate mass, volume, and density using this equation. And if it helps, know this triangle. Know it, because it will make life so easy, right? You put M for mass, volume for V for volume, and D for density, right? And so if you're looking for mass, you know volume times density gives you mass. If you're looking for density, you know mass divided by volume gives you density. And if you're looking for volume, you know that mass divided by density gives you volume. right? So that's going to end the lesson for today. Hopefully, it was helpful for viscosity and density. Again, density and volume will appear on a test, and you need to know how to calculate density. You also need to know what viscosity is. So you need to know what viscosity is, which is how easily molecules in a liquid or gas move past each other. You need to know what affects viscosity, the thickness of the liquid, as well as the temperature. You need to understand that flow rate is basically the opposite of viscosity. If you have a high flow rate, then you have a low viscosity because the molecules can move past each other easily. And if you have a low flow rate, you have a high viscosity because the molecules don't move easily past each other. Knowing how viscosity can be used in society is helpful, and understanding the applications of viscosity and as well as density later on. You also need to understand that large molecules bump into each other, so they'll have a slow flow if they're a liquid, and so they'll have a higher viscosity. You also need to know how to change viscosity. You need to know that heating liquids, keyword here, heating liquids decreases viscosity and increases flow rate. And you need to know that gases have the opposite rule. Heating gases increase their viscosity and decrease their flow rate. You need to know why that's the case. And all you need to know is gases have already so much energy that they bump into each other more when you heat them. And so their viscosity goes up because they can't move past each other because they're so energetic, they're crashing into each other. You need to know density again. Yep. You need to know what it is. You need to know which type of matter, what state of matter has the most density. Solids have the most, gases have the least, and liquids are in the middle. And that is because as you add energy to a substance, the molecules and particles will make up more space, take up more space, and so they'll become less dense. That covers that, and you need to know the equation and triangle that I drew for density. So hopefully that was helpful, and I will see you next lesson.